CLion a cross-platform IDE for C and C++. Download now.
Hello everybody, my name is Mostafa Mahmoud. I'm a senior C++ engineer with more than 10 years of experience, and today I want to share with you my journey of building a property viewer for C++. So before we start, let's start by defining first what is a property. Traditionally, properties are special kinds of class member that provide a way to read, write, or compute the value of a private field. Properties are used to control access of the data of an object while still using a simple and intuitive syntax. They provide a way to define the behavior when accessing or modifying a class member, and um, they can encapsulate the logic for validation, lazy loading, or other side effects. While many modern programming languages such as C Sharp, Swift, and Python offer robust built-in support for properties, C++ has traditionally lacked formal property support. This absence has implications for developers, making certain design patterns more cumbersome and leading to the need for custom solutions. Multiple libraries tried to address this issue and implemented ways to define properties on top of C++, but the lack of formal language support for the concept meant that each of these implementations works in its own ways, and that there is no specification that defines exactly how a property in C++ should be declared. So let's talk about the thing that led me to talk about this topic in the first place. I've been working on a reverse engineering toolkit that facilitates dynamic analysis of software samples at runtime. And this was supposed to be a small side project, but over the past 3 years, I've been adding more and more features to this toolkit. And this project is what drove me down this path. At first, my toolkit was very simple. I just had the ability to load the software sample and inject some code to be run inside the sample memory space. Then I wanted to have the ability to analyze the sample executable and get to see as much information about it as possible without even running it. Stuff like what C runtime library does it use and what compiler was used to create this file. This was as simple as using a table view with two columns to display this information. Nothing complicated about this. But after then, I started experimenting with different techniques of running external code inside the process of the sample. Each of such techniques can be customized in different ways. Like, for example, if I wanted to use a debugger or modify the execution path of the original code, or wanted to use memory caves or DLN injections. So I created a new table similar to the first one, where each loading option is displayed in a column and its value can be modified in the other column. I also added the ability to browse for files and folders in the table for some values, since multiple values were just paths, and copying and pasting a path to a file or a folder is just annoying, and I'm lazy. Then I wanted to add support for analyzing Qt-based applications. So I needed a way to display and modify the properties of both QObjects and QMetaObjects at runtime. This control worked very well, and I made it extensible so that I can add support for displaying values of properties with custom data types that I never encountered before. This was working very well at first, but I continued adding support for more and more types. And then I started feeling the shortcomings of my design. Every now and then I need to add support for a new data type, and I would take some time to remember how exactly this control worked internally and where exactly should I add the new editor for my new data type. And it became a nightmare when Qt6 introduced the QProperty class. I wanted to support viewing it in my control, but I realized that my system was totally built for Qt5 and relied heavily on how it does reflection. If Qt decided to change their meta system, my control would become obsolete. After a while, I wanted to add support for retrieving RTTI information from the analyzed samples. As you may know, RTTI stands for Runtime Type Information. It's a feature that allows the type of an object to be determined during program execution. It provides mechanisms to identify the exact type of an object and query the object properties and safely cast types at runtime. This is particularly useful when dealing with polymorphic objects and ensuring type safety and type casting operations. Each time, every time you use type ID or dynamic cast or std type info, you are basically using RTTI. This information exists in many executables, and I wanted to be able to make use of it. At this point, also wanted to be able to group the set of functions that access the same member under the same group and have the ability to rename individual functions and groups. So I made a new control that is simpler than the one for QObjects, but has support for tracing pointers and grouping them together under different groups with a dynamic dispatch mechanisms that calls the getter to retrieve the property value and the setter function when the user changes the data in the UI. All this was already getting out of control, and I also encountered other software samples that relied on totally different mechanisms for implementing properties in C++. With each system I want to support in my toolkit, I ended up either modifying one of the already existing viewers or implementing a totally new one that works only with this special case. This was frustrating, and knowing that C++26 will have reflection meant that it's just a matter of time before everyone starts implementing their own property systems that rely on reflection, and my already bad code will become impossible to maintain. So I started looking into available options that I can use to cover all these use cases. Surprisingly, I couldn't find much, only three solutions that were good enough for me to even consider as viable options. First one was called Qt Property Browser. I'm not sure about this, but I think it was originally implemented for Qt4, as it was trying to implement a lot of the tree widget features that exist by default in the Qt widget in Qt5. Also, I couldn't find any documentation for it, except for a simple page that shows how to use it to display properties of QObjects using it. This page was on the old Qt forum, and aside from this, it relied heavily on deprecated Qt functions, and definitely didn't support Qt6. It had very ugly API that required the user to deal with row pointers and allocate objects in the heap by hand. Plus, it was less maintained in 2015. As you can see in this list, it was basically not what I'm looking for at all. The second solution was a library called Qt Property. This library was huge and had lots and lots of functionalities and required a lot of learning from the user just to get it to work. Beside this, it had a poorly structured API and wasn't straightforward to use, and it was last maintained in 2021. The third option was the property editor of the Qt designer. This was a very solid solution, but it was an internal component of Qt designer, which meant that it wasn't available as a standalone library and that it lacked a stable API and proper documentation. Also, it could only display properties of QObjects, so displaying a list of properties that are defined declaratively wasn't an option. Um, so as you saw, none of these options was able to cover my needs. All of them have more cons than pros, and based on this, I wrote down the requirements of what the ideal solution should look like. So this is the list that I came up with. As you can see, my solution should be able to display properties from C++ objects and also properties defined in a declarative way. It should be minimal, so I don't want my solution to be very big. It had to be extensible and customizable. It had to have a stable API, so that it is future proof. I needed it to be hard to misuse by design. Also, it had to support Qt5 onward, so Qt6, Qt7, whatever. It would be a nice to have if it was something that can be easily ported to other UI frameworks. Also, I need it to be very simple, that it needs no experience to use. Also, with the property attributes, I needed this system to be type safe because none of the previous solutions had the type safe attributes. It had to be it had to provide some customization for the UI editors for different data types and be able to group properties by categories or display them as a simple list. Um, I also needed to be lightweight and have little to no footprint on existing code bases. So I don't want anybody using my solution to be to have to modify their code base to be able to use it. And the most important thing, it should never rely on macros. Um, so based on this, I started looking into available solutions that are available in other languages since I already exhausted my C++ options anyway. The one that instantly popped into my mind was the property grid control from the Windows Forms controls in the .NET ecosystem. This solution had a tool. Basically, everything that I was looking for was in this control. The only exception is that it's not easy to display properties of stuff that aren't based on QObjects, on the object class. So displaying dynamic properties, for example, external user properties defined in a JSON file, this wouldn't be easy. Based on this, my logic was, okay, maybe I should just port this solution as it is to C++. But sadly, it's never that easy. The property grid control totally relied on the C# reflection capabilities and excellent property system. It owes its robustness to these two core components of the language, which we have nothing like in C++. This meant that my solution will have to bridge this gap, and well, this wasn't an easy task at all. If I choose to totally rely on the reflection system of Qt, this will make it limited to displaying the properties of QObjects and QGadgets. This definitely isn't reasonable and makes no sense at all. And it contradicts this requirement to have little to no footprint or require no modification for existing code. Um, I started looking into available standalone reflection solutions like RTTR. And the problem was always that all of these libraries don't work without changing the syntax of existing code, plus they rely heavily on macros. This meant that reflection is actually off the table and I should start thinking of something better. Qt has the Qt variant class, which is arguably a better version of the std_any class. It doesn't require making any changes to the existing code. Also, it has the ability to do runtime conversions from and to any data type using the magic of templates. Plus, it's already used by Qt everywhere. Actually, the reflection system relies totally on this single class. And I'll have to use it anyway to display data in my control because I'll be using a Qt view. So this looked like a very promising route to look at. Plus, my QObject property viewer was totally reliant on QVariants, so I knew firsthand how powerful this class is. Um, so I wanted to see how far can I go using the Qt variant class. Um, I wanted to start simple, so I built the simplest form of this control with just 2 or 3 functions in the property grid class, which I can use to write real-life test cases. Based on this, I'll keep refining my design and simplifying my implementation until I reach a stable point where I have something that works as intended. I also had to build some real use cases to be able to assess how effective my solution is. Um, this meant that having a simple and stable API was a very good idea. This is what I started with. As you can see, nothing fancy, just the simplest interface possible. Um, just a function to uh, just a function to add properties and another function to add property editors. I started building my use cases on top of this simple stable API and worked my way backwards in figuring out all the implementation details that can make such API work as intended. I wrote real life use cases for adding properties and customizing property editors for different data types. These are the simple test cases that I wrote on top of my simple API. As you can see, I can add a property with a name and a value. This is the simplest form. I can add some attributes to each property, like the category or the description, as you can see here. I also can add a property with multiple attributes, as much attributes as I want here. When I want to extend my property grid control to support dealing with different data types, I wanted to make sure this is as simple as possible. So all the user will have to do is, just as you can see, subclass the property editor class and override the can handle method to let the property grid know which properties you will be able to handle. Then implement the toString and FromString functions if you want to represent the property value as a string in the UI. Then you add your subclass to the property editor to use it with all properties, all the properties that it supports. Or you can create a simple property and then provide it with the property editor attribute and provide your customized editor um, if you wanted to use it with some specific properties only. For the UI, I tried to keep it as simple as possible. This is how the property grid looks like. Just a simple table with with nothing, with the only two columns for the property name and value. Also, there is the option to display the properties as a simple table or categorized. Um, if you remember the category attribute from earlier. At the bottom, you have a small area that displays the description of the currently selected property if it had a description. This is the description attribute that I showed earlier also. Any property can be either edited through a simple plain text box or a text box with a button next to it for the user actions like browsing a file or a font, or a drop down for properties with multiple choices for value or complex data types like colors. The drop down display allows the user to either get a simple drop down list, so just like this, with multiple values to choose from, or a more complex widget like a date and time picker or a rich text editor for editing formatted text like Markdown and HTML, just like the one in the picture. Any widget can be displayed here. Um, the property editors can also provide a preview icon to be displayed next to the property value. Such capability is useful when dealing with values of types such as images, fonts, colors, all of this. So how does the API for all of this look like? For all of this to work, I had to implement a property class that I can use to hold the property name, type, and all its attributes. The property struct is a very simple struct. It contains nothing but the property name and the property type and a list of attributes. For now, that the type is the simple value of calling the templated Q meta type ID function for any given type. The structure is copyable, movable, and default constructible. Attributes can be added through the add attribute function, both at compile time and at runtime. The attribute class is non-polymorphic, so you can't extend already existing attributes. You can just create new ones. Attributes are not enumerable for now. Maybe in the future we can add the ability to enumerate them. I don't think this is something that we need to do, but Also, as we said before, the attributes that are stored in any object are not enumerable, so you can't just get the list of all attributes of a property, but they are queryable by their type. This means that you can ask any property if it has an attribute of a specific type and then get the value of this attributes if it has one. As you can see in this example, I can use the has attribute function to check if a property has a description attribute. And and if so, I can just get its value using the get attribute function. If you called get attribute for an attribute type that the property doesn't have, it will return the default value for this attribute. That's why any attribute should be default and copy constructible. The choice to make attributes copyable was deliberate so that the user doesn't have to worry about object lifetime management. To make sure that only copyable and default constructible attributes are passed to the user templates, template parameters are guarded using templated const expert functions instead of concepts to support all C++ standards prior to C++20. We'll talk about more about this in a moment. Using const expert checks to ensure that meaningful error is basically meant to ensure that meaningful error messages are displayed to the user when he passes invalid template parameters. We need to force the linter to perform the required checks on user provided template parameters and display the error and display the error for the users directly in the same line where he used the templated code. So just like this. Um, at its core, template checks is a composition of simple templated const expert functions that would raise a static assert if the template parameters constraints were not met. So just like this, as you can see here, nothing fancy. You just check if if the template parameter inherits the attribute class, and if not, it will just raise a static assert. To force the compiler to use our const expert checks, we can just do this. We add an extra template parameter with a default variable. So with a default value that is an integral constant, and we call the const expert templated function is attribute with the main template type, which is t in this case. The compiler has to evaluate the value of the second template parameter, which means it will call the is attribute function. And if the user supplied a type for t that doesn't inherit t, is attribute will do a static assert, and since the static assert occurred in a const expert function, the linter will stop immediately and will display the error to the user at the line where he supplied the incorrect type. This works with linters that are based on Clang, but for some reason doesn't work with Visual Studio linter, but at least it produces readable error messages. As you can see, this is very long and not easy to understand at first glance, but we can solve this by hiding all these details behind the templated using statement like this. So nothing fancy, we just move this part into this templated using statement. And now we can simply rewrite our code like this. As you can see, this is much cleaner and way more readable. Even someone who doesn't have enough knowledge about metaprogramming can easily get what this code does. Also, it makes it really easy to chain multiple template checks at the same time without compromising the readability and maintainability of the code. So why not use hard substitution failures or SPINA with simple static asserts to do compile time checks for template parameters? The problem with both techniques is that the user has to dig deeper to find out which usage of the templated code caused the error, as usually compiler errors that are emitted from such techniques are very generic errors with little to no information about what exactly is the problem. and the user ends up with a multitude of ugly compiler errors in header files that he had never even knew about their existence. As you can see here, that's just the beginning of the error message. The const expert template parameters checks provides similar functionality to concepts in C++ and modern C++, but with the ability to work nicely with older code bases. This can work with C++ 14 onwards. Unfortunately, that doesn't work with C++ 11 as template arguments, the deduction requires default type arguments to be a valid type. Um, let's talk about some advanced use cases. Most of the time, the user wants to just display some properties and get notified when the user modifies their value in the UI, but this isn't the only use case. What if the user needed to display a property of a specific object and needed to have access to this object to decide how to display the property editor for this specific property based on another property of the parent object? Whether, for example, whether to display the suffix um, point or pixel for window font, for example, or maybe the user wanted to display the properties of multiple objects at the same time in the same property grid. All these niche use cases can be implemented easily if there was way to pass the object that owns the property with the property itself. This is where the second overload of the property grid add property function comes in. This overload allows the user to pass the instance of the object that owns this property alongside the property itself. So as you can see here, we have this add property, and you pass it this property object itself, not like the first overload. You create a property and then you pass it to this. Then you pass the value for this property, and then if there is an object that owns this property, you pass it as the third object, the third parameter. This is an example of such option and where it becomes really handy. In this example, we need to have a property that we can use to display or modify the window state for an application settings in Qt. We will need to create a QSettings object and configure it with the format, the scope, and then the organization name to be able to read write the window state value. We can create a simple property with the value. So here is the property. And we pass the value that we retrieved from the QSettings object. We get this value and we pass it to the add property function. But we will have to recreate the same object with the same proper parameters if the user changed the value in the UI and now we wanted to save it back into the QSettings. This obviously isn't very good at all, and things will go out of control very quickly once we start adding more properties like these. Imagine an application with 100 different settings that has different scopes and are stored with different formats. This is where the object parameter comes in handy. We can just associate the object that we use to get the property value with the property itself and write a very generic. So as you can see here, this is the object that we use to get the property. So we passed here. And now we can write a very generic slot that knows how to store the data of any value with the property itself without the hassle of figuring out what settings object is what. As you can see, we just access the context, the property context, and we get the user settings from the context object function. Now we can just use this user settings to set the value using the property name and the new user provided value. You don't have to worry about it if it doesn't make total sense now. Usually this is a very powerful tool that you will never care about until you need it. Now let's take a look at the full interface for the property editor class. Um, it's a simple, concrete implementation, so no pure virtual functions that already knows how to convert all basic data types from and to strings. The design decision for having a concrete implementation was made to give new users the ability to incrementally discover how to achieve the desired look and behavior for their custom editors through rapid iterations. This simple design doesn't require any kind of understanding really about the details of how the property grid control works internally. You only pay for what you need, uh, kind of thing. The function names are simple and descriptive. The user can safely override the behavior of any function without worrying about re-implementing the remaining functions to accommodate his change. This point is really important as none of the other alternatives that I showed earlier had. They all require the user to re-implement multiple functions if they wanted to customize a single aspect of the editor. The default implementations are generic enough to be able to handle any user implementation safely, so it wouldn't complain about any unknown behavior or data types. And again, this was intentional to make sure that it's hard to misuse by design. As you could see in the property editor interface, all its function receive a class called property context. This class is a very simple structure that groups properties with the property with its value and its owning object. So the user has the ability to get any piece of information that he needs to know about any property from a single place. Somebody might ask why introduce a new class? Can't we just pass the property alongside its value and owning object as extra parameters to the functions that needs them? And the reason is that passing the property value and its owning object as extra parameters to all these functions that can make use of this information poses a scalability issue. What if we decided to change the type of the value parameter from QVariant to std any, for example, in the future? Now all objects that has an existing implementation for custom property editors will fail to compile, as the signature of the functions that they are overriding wouldn't match the signature of the function in the base class. What's worse is that if some implementation was not making use of the property value, they will have to change their code, as it will also fail to compile against the new API. They will have to update their code base because of something that they never used anyway, and will pay for something that they never needed in the first place. Plus, grouping all the parameters in a single class that gets passed everywhere basically eliminates this problem altogether. So it's basically still following the you only pay for what you need for concept. Um, then why can't we just add the value of and the object as extra fields in the property class itself instead of creating an extra class to group all of this? Actually, this was the initial design, but unfortunately, this meant that there was no good way to hide all the unnecessary complexities and implementation details from casual users who just want to add a simple property just by providing a name and a value and maybe some attributes. There was no clean way to keep the object parameter and the attribute parameters hidden from the user who just wants to create a simple property with a name and value. This was a very good example of how the combination of functions overloading and templates and optional parameters and variadic arguments is the recipe for disaster. So now that we discussed all the different parts of the system, what did we end up adding to the original API for the property grid? And surprisingly, not much. As you can see, this is the original API that I showed earlier, and this is the final API. So I basically didn't change anything. I only had to add new two extra functions to the original API. one overload for the add property. This overload that takes a property object and a value and an optional owning object, and a signal for handling user changes to the properties in the UI. So now these are the final components of my library, or the complexity is built on top of these. Um, just five classes. The attribute one is just an empty struct. Also, the property context will never the user will never need to instantiate this directly anyways. I just made it part of the public API to allow users to write unit tests for this for their own property editors. So I made its constructor public for this. So in total, just five classes, one of which is an empty struct. The casual user will only need to interact with the property grid class to be able to build whatever he wants. And most users will never even need to know about the existence of these other classes to be able to use the control for the first time. For advanced users and advanced use cases, the user doesn't have to know about anything that he will not use for his specific case. Almost all real life use cases can be covered using these very same ports. Also, as an added bonus, the library is almost fully portable to other GUI frameworks. You can implement your own property grid on top of the library core using whatever GUI framework that you want. We just need to replace the QVariant class with an equivalent class that has the same features, and we will be totally ready to go with any UI framework. So what are the future plans for this library? Currently, users can't display subproperties for complex data types like vectors and QVector 3Ds and points and colors, for example. So you can just see the X, Y, and Z components for a QVector 3D as subproperties of it. Support for this feature is planned, but not critical for now. Also, we don't have yet any support for UI localization and translation, but this is something that I'll be working on. Maybe also we can add support for pair property context menus. It sounds like a nice feature, but I'm not sure if it's worth all the time and effort. Um, Maybe we should also implement a property grid for control for QML. I don't need it right now, but if anybody needs that, you can just reach out to me to work on that. I think also at some point I will have to write a port for the property grid class that works on top of MGUI, as this was originally developed for my reverse engineering toolkit, and the game modding community makes heavy use of MGUI. Um, this last one is like maybe we can implement our own replacement class to remove the reliance on QVariant and make this library totally portable for other GUI frameworks. Um, but this is definitely a very big task that it will make but that will take a lot of time and effort, and I'm not sure how are we going to how would we achieve this yet. But I think I'll be working on this. Um, so you can check out the code on GitHub through the following QR code. Um, Also, you can reach out to me through my email or my LinkedIn using these links. Thank you very much for listening, and see you soon.